All right. OK, so this work is about two techniques for dealing with randomized algorithms. So the first technique is for amplification. So here the situation is that we have a randomized algorithm with error probability 1/3, and we want to reduce the error probability to exponentially low in some parameter k without a large blow-up in the runtime. So usually when we try to amplify an algorithm, what we do is we just repeat it k times, and then we get error probability exponentially low in k. And we show how for certain algorithms we can actually amplify in a completely different way that doesn't blow up the runtime by a factor of k. And then the second technique is a technique for derandomization, so converting a randomized algorithm to a deterministic algorithm. And then in the paper, we show applications to a bunch of problems, like these ones. So for example, so approximating CSPs on dense graphs, for example. All right, so in the talk, I'm going to go over the two techniques, the amplification and derandomization, like at a high level. And so let me start with amplification. So before I get to amplification, let me talk about the high level of what's going on. So it's useful to compare what we do to Adelman's theorem. So Adelman's theorem states that BPP is contained in P/poly, and this is sort of the way it works. You start with an algorithm with error probability 1/3, and then you repeat it O of n times to amplify it to error probability exponentially low in n. And now because there are only 2 to the n inputs, we know by the union bound that there's a random string that works for all inputs, so we can hard code it into the algorithm. Cool. Now there are a few weaknesses about Adelman's theorem. So of course, the obvious one is that it gives us non-uniform algorithms. But sometimes in algorithms, that's fine. There are some problems in algorithms where a non-uniform algorithm may imply a uniform algorithm. Minimum spanning tree is one of them, which is also interesting because there's a randomized deterministic. Well, our best randomized algorithm is faster than our best known deterministic algorithm. Cool. And another weakness in Adelman's theorem is that the final algorithm that we get is a factor of n slower than the original randomized algorithm. So we try for certain algorithms to, when we apply something similar to Adelman's theorem, avoid this O of n blow up. Cool. So this is sort of what we do. So we start with, similarly, an algorithm with error probability 1/3. And then we use our amplification step, so we don't have to do repetition. So that's one way in which we improve over Adelman, is that we amplify without repetition. And then the other thing is that we end the amplification step earlier. So in Adelman's theorem, we amplify until our error probability is exponentially low in n. And what we do is we stop at some k much smaller than n. All right, cool. So we'll do amplification first, and then we'll do derandomization. Cool. So once again, we have an algorithm with error probability 1/3, and we want to decrease the error probability without using repetition, so without increasing the runtime too much. Cool. So here's vaguely the idea. So in some randomized algorithms, there's some quick, efficient randomized test to see if a random string R is good for the algorithm. So to see if there's a random string R so that A succeeds with R. And we're sort of going to use these tests to find an R so that A of XR succeeds. So at the high level, we sample an R, then we run a bunch of tests on R to see if it's good. If it looks bad, we throw it out and try again. And if it's good, then we run A. So the thing to note is that we're spending some time testing if R is good, but at the end, we're running A only once. So unlike in repetition where we run A multiple times, here we spend some time looking at R, and then we run A once. So I need to explain what I mean by these quick, efficient, randomized tests. So I'm not going to define exactly what they are, but I'm going to show an example of one of them. And it's going to be a slightly silly example because it'll be an algorithm we already know how to derandomize, but it does a good job explaining what I mean by one of these efficient tests. So suppose we're looking at quicksort. So sort of what we do here is we pick a random pivot, and we want it to be near the middle of the list. And with constants or with some probability, it's going to be on the side, and that's not good. Okay, so here's a way to sort of check if a pivot is near the center. So we pick 2 other random elements, and we check if our pivot is in the middle. Now, if our pivot is in the middle, then we gain evidence that our choice of pivot is good. And if our pivot is not in between the 2 elements, then that's evidence that our pivot is bad. So vaguely what we're going to do is we're going to use these tests. So we're going to pick a random pivot and then apply some of these tests until we're either fairly certain that the pivot is bad and we throw it out and try again, or we're fairly certain that it's good. Okay? And there's this trade-off here. So running this test only once only gives us constant probability, which is not very good, but on the other hand, it's very efficient. It takes only O of 1 time. And then on the other hand, if we want error probability exponentially low in n, we can run this test n times, but then that takes a long time. And it's especially bad if we run it n times on a bad pivot, and then we throw it out and we wasted O of n time. Cool. So we want to sort of solve this trade-off. So the way we do it is we look at this other problem, which is an abstraction of what we had before, of like the quicksort example and randomized algorithms in general that have one of these efficient tests. So here it is. We call it the biased coin problem. I think it's an interesting problem on its own as well. It's very simple. So you have a big pile of coins. We define the bias of a coin to be the probability that it falls on heads. And you know that 2/3 of the coins have bias 0.9. And your goal is to find a coin with bias at least 0.8 with probability like 1 minus x minus n. And you want to do it with as few coin tosses as possible. Okay, so let me explain how this is related to randomized algorithms and amplification. So here's sort of the analogy. So a coin represents a random string. So the big pile of coins is sort of the pile of random strings, and we can pick one out. And then a coin toss is like a quick test. So sort of like a quick test gives us evidence about whether a random string is good or not. Oh, yeah, so a quick test gives us evidence about the random string, and a coin toss gives us evidence about a coin. So that's sort of the analogy. All right, and so how are we going to solve the biased coin problem? So first, let's look at the naive solution, which actually gives us runtime O of n squared, which we'll later see how we can do better. So what we do here is we pick a coin at random, we toss it n times. If more than 0.85 of the tosses are heads, we keep it, and otherwise we restart with a new coin. Now, it's easy to see that we get error probability x of minus n, because by the turn-off bound, if we toss the coin n times, more than 0.85 of the tosses are heads, then like we're quite confident that the bias is at least 0.8. Okay, so now we want to beat this. Ideally, we want to get something like O of n. And right now we can get O of n log squared n. And I'm not going to show the general algorithm, but I'll show it for a slightly different problem. So it's just like a simpler case. So in the simple case, similarly, we have a large pile of coins. 2/3 of them have bias at least 0.9, and we want a coin with bias at least 0.8. And we also have this added assumption that there are no coins between bias 0.9 and 0.8. So each coin either has bias less than 0.8 or more than 0.9. Cool. All right, so here's the algorithm. We pick a random coin, and we toss it 2 to the I times for I from 1 to log n. And at each step, if fewer than 0.85 of the fraction of the tosses are heads, we throw out the coin and start with a new one. So vaguely, the idea here, compared to what we had before, is that in the previous algorithm, we could have taken a bad coin and tossed it n times and then threw it out. So then we wasted a lot of time on a bad coin. But here we sort of guarantee that we're not going to toss a coin many times without throwing it out. So vaguely, the analysis is that the probability that at the kth phase we restart is exponentially low in k. So the probability that we waste k tosses, so that we toss a coin k times and then throw it out, is exponentially low in k. So you can analyze it and see that this takes O of n tosses. Now, for the general case of the coin problem, where we don't have this promise about no coins between 0.8 and 0.9, this algorithm doesn't quite work, because if we have a coin with bias like exactly 0.85, then it turns out it's like still kind of likely that it will get thrown out in the late phase. So it's likely that we'll spend a lot of like tosses on it and then throw it out. So vaguely, what we do in the general case is that we, instead of having like a threshold like 0.85, we have a different threshold for each one of the phases. We just lower the threshold every time. And like after some analysis, you see that you get O of n log squared n. Yeah, the best lower bound we have on the biased coin problem is just like the trivial O of n. So yeah, I think that's interesting. All right, cool. So to summarize what we did for amplification, we had an algorithm A with probability 1/3. We wanted an algorithm with lower error probability. So we saw that some algorithms have these efficient tests to test if a random string looks good or not. And then we can run some sort of, like some version of the biased coin algorithm to find a string R that's good, and then we run A only once. So sort of the takeaway here is if you have an algorithm and you're trying to amplify it, and repetition is too slow, then another thing you can do is just try to create an efficient test. And then by the coin protocol, then this will like efficiently amplify your algorithm. Okay, great. So back to the high level. So we started with an algorithm of error probability 1/3. We amplified it, and now we want to show the derandomization technique. Oh, and the thing to note is that the derandomization technique gives us non-uniform algorithms at the end, but the amplification step doesn't. The amplification step just like it gives you a normal algorithm. It takes in a normal algorithm and gives you back like a standard uniform algorithm. Cool. So derandomization, algorithm with low error probability to a deterministic non-uniform algorithm. So here's the idea. So if the error probability is exponentially low in some k, we'll partition the inputs into x of k subsets so that the randomized algorithm behaves similarly on inputs in the same subset. And then what we do is we're going to apply the union bound and show that there exists a random string that works for all of these subsets. Then we hard code it in, and we're done. So sort of like to compare it again with Adelman, needs error probability exponentially low in n. We only need exponentially low in k because we partition the inputs into these subsets. So how are we going to like partition our inputs into subsets where the algorithm behaves similarly? So vaguely what we're going to do is we're going to sketch each input with k bits. So the way to think of a sketch is sort of some sort of like lossy compression. It's like what we usually think of as a sketch. So in the paper, we often just use some sort of subgraph. Where input is a graph, we use some sort of smaller subgraph. Things that might be interesting to use here in the future are like spanners or sparsifiers or stuff like that. Cool. So, all right. So back to how the de-randomization works. So we can think of a randomized algorithm as like a big table, inputs at the top and randomness is on the left. And then in each one of the little cells, we like have a check mark if that randomized algorithm succeeds on that input with that randomness. Cool. And then like we have an x if it doesn't. So what Adelman's theorem tells us is it tells us that if our error probability is exponentially low in n, so in each one of the columns, like all but an exponentially small fraction are check marks, then there exists a row with all check marks. Cool. So we want to do better than that. So what we do is we partition the inputs into inputs with the same sketch. And then, so now for a second, imagine if for any two inputs with the same sketch, the algorithm behaves identically. So for any two columns that are in the same box are identical. Okay? So what happens in this case is that we only need an error probability of x to the minus k instead of minus n, where k is the sketch size. Cool? All right, so if the columns are identical, columns of two inputs in the same sketch are identical, then we need a much, we don't need as low of an error probability. All right, great. And in fact, we need something weaker. We don't need that the columns are identical. We just need that in each one of the boxes there are many rows where it's full of check marks. Okay, cool. So of course, not all randomized algorithms can be partitioned in this way so that the rows are similar enough. But one of the contributions of the paper is that we show a way to argue that situations like these exist, and then we find actual randomized algorithms where we can make this partition. Okay, cool. So, all right. So how do we argue that a situation like this exists? We construct these things we call oblivious verifiers. So here's the definition: an epsilon oblivious verifier is an algorithm that gets as input a sketch and a string r, and it satisfies these two conditions. So first of all, for all x and r, if the verifier accepts on the sketch and on r, then on a succeeds on the inputs x and the randomness r. And for every sketch, the probability that the verifier accepts is less than epsilon. So vaguely what an oblivious verifier does is it gets the sketch of an input and an r, and it tells you if the original randomized algorithm succeeds. So cool. All right. And the observation is that if there's an oblivious verifier with a small enough epsilon, then by the union bound, there's a randomness string that we can hard code into the algorithm, like in Adelman. So vaguely, the way to think of another way to think of an epsilon oblivious verifier is if we think back to the table we had a couple slides ago. An epsilon oblivious verifier means that in each one of the boxes of inputs with the same sketch, all but epsilon fraction of the rows are full of check marks. Okay? Cool. So why are oblivious verifiers great? So now we've turned, so we started with some de-randomization problem. And now what we're trying to do is just construct one of these oblivious verifiers. And the nice thing about an oblivious verifier is that there's no limit on the runtime of an oblivious verifier. So the oblivious verifier can be very inefficient. Similarly, constructing the sketches can be very inefficient. So in the paper, for some of our examples, we construct the sketch using the probabilistic method. So we don't actually have any good explicit constructions. Okay, cool. So that's what's good about an oblivious verifier. And on the other hand, what's hard about constructing the oblivious verifiers? So the main challenge is sort of that the randomized algorithm might branch depending on the input. And the oblivious verifier doesn't actually have the whole input. The oblivious verifier has only a sketch. So if the algorithm reaches some if statement, the verifier might not know if the input satisfies the if statement or not. but somehow we still have to argue about whether our algorithm will succeed or not. Okay, cool. All right, so the solution here is that the verifier just like tries all possible branches of the algorithm. So if there's an if statement and the verifier doesn't know, it just like tries both. And that's okay, because the verifier can be inefficient. So it can just like try all of the possible branches and see if they succeed. All right, cool. So that's oblivious verifiers. All right, so to summarize, was the amplification step. There's the amplification-like technique, where we ran efficient tests to see if our randomness was good or not. And the takeaway there was sort of like, if you want to amplify an algorithm and you don't want to use repetition, another thing you can do is try to like create these quick, efficient tests to see if your randomness is good, and then you'll automatically like get your algorithm amplified without like much slowdown in your runtime. And then there was the derandomization, which is if you are trying to derandomize an algorithm, another thing you can do is like try to construct some sort of sketch and some sort of oblivious verifier, and that will give you a non-uniform algorithm. And some hopes for the derandomization technique are maybe minimum spanning tree. So a reason minimum spanning tree specifically seems promising is that we already have randomized algorithms with very low error probability. So Karger, Klein, and Tarjan give an algorithm with error probability exponentially low in M, the number of edges. So that means our sketch here can be quite large. It can be like M, the number of edges, bits, like M bits. And in addition, for minimum spanning tree, a non-uniform algorithm would imply a uniform algorithm. So pretty much, like, if someone would construct an oblivious verifier in a sketch for minimum spanning tree, then like that would resolve that problem. All right, cool, thanks. What's up? Yeah, it was at the, near the front. Yeah. They're fairly complicated. A lot of them are just, what? So we mostly just like either give different algorithms that don't improve their running times. For free games is the only one where the running time actually improves, and it's just like in the dependence on epsilon and delta. Like these improvements aren't huge. They're mostly just like to show the use. Yeah. Well, yeah. I mean, it depends on what like parameters you use. Yeah. Like there are certain like choices of parameters in which these give improvements. It's just like, maybe I'm confused.
To understand if there is a certain, for example, if it's a space-bounded algorithm, or if it's the randomness is accessed in a certain way, then you can have a speed up. Is Merton possible?
I don't know. Like, I don't know. I don't see how to. Yeah. All right. Awesome.